Okay, in this video, we're going to review ePOP for a main battle tank. This is a tracked vehicle, and the customer, in this case, wants to know if a hybrid solution can outperform the legacy powertrain, diesel powertrain, in swap analysis, specifically volume. They need both extra power and extra room to fit some new weaponry. So what we've done, in addition to taking the drive cycle, which we just did a cruising power for the track drive, added an electric cycle, which is a nominal low level, but then a 100 kilowatts. This is a new requirement for the next generation, that it has to be able to do a 100 kilowatts peak electric generation. And then we added a steering load, which isn't much, but we wanted to account for it in the powertrain, since it is significant. It is a significant load when it does occur. So added some power there to account for the steering. From here, we'll move on to the configurations. This figure here represents the current configuration, both the legacy configuration, and if it were to be a parallel hybrid, it can represent that configuration too. So the engine powering the track drive, which is the most significant load, through a transmission, and each one of these icons in the configuration is represented by the technology that you see over here. So in this case, the transmission is cross drive in the defense. So that has been characterized in the component library, that this transmission. We can go there. You see all the different components in the library. So the cross drive is cost, volume density, mass density, and efficiency have been characterized based on public data that's available, and those characteristics then get implemented in the configuration. Here too, you can see the e-drive motor and transmission combined together. The characteristics of that'll come in useful for series configurations. So this is a parallel configuration. These are the technologies applied through the power flow, through the powertrain configurations. Next, we'll move on to the series configuration. Now, it was a little bit more advanced because the technology applied to the track drive is different than the motor technology applied to the steering. In this case, we made the steering an electric steering, since we were making the series, and the parallel version, the steering was done hydraulically. You can represent it different ways. It could be an e-pump to do that. There's different configurations you can see, but they all have impacts. These configurations have impacts on the efficiency, the volume, the mass. And so we consider all of those configurations that you can see here. There's 9 configurations available to choose from to accomplish these outputs that are required. So let's look into some results. What we have here on the right is, even though we have the configuration and the technologies, we don't know what the optimal size of, say, the hybrid battery would be. There could be many different sizes, and those drive different energy and power characteristics. So since ePOP doesn't know what will be the optimum answer, it solves for all battery sizes up to and including making the vehicle, the powertrain, 100% battery. Now, in a lot of cases, and this is a good case, a very heavy main battle tank, it doesn't make sense to do a battery only. You can see here the difference in volume to achieve the same achieve the same range and performance, the volume of making it a battery only, I mean, is going to be 4 times the volume of making it hybrid or the legacy. So same with we're looking at volume here. That's one KPI, but mass, is similar, going from ICE only to battery only. This doesn't make sense. Customers not looking for battery only solution in this case. It's nice to be able to quickly reference what it would be if you had a battery only. An answer that it's not feasible is just as valuable as what is feasible. So ePOP solves for all battery sizes and electrification configurations here, so that you're seeing A versus B show up on this line. Next, we're going to look at some results. So it gives us a little bit finer resolution on the differences between the powertrains. So right now, the dark line is on this is the legacy powertrain, and this one here is actually a series hybrid that you see the configuration, down here. But it seems as though, and this is a dynamic swap analysis that you can see, as you add batteries to the series up until this point here, you're actually able to achieve a local minimum on the volume, essentially the same volume as the legacy, by decreasing the transmission but increasing the motor, increasing the battery. So increasing the electrification here, you're able to downsize the ICE and actually achieve the same fuel economy, not really changing the tank size that much, 13 liters, which is negligible in this case. But this is able to achieve the 100 kilowatt electric power load. So it's nice to know what the trade-off is between the two architectures, and also if you did want to increase the battery size, notice at this point you're really no longer getting any engine downsizing. Engines staying the same size because this is not a plug-in. All the energy has to come from the engine. So adding more and more batteries after this point doesn't really get you any more engine downsizing. Here's where you maximize engine downsizing with the battery size. In this case, is a 203 kilowatt hour battery pack. You can see here the details of this configuration, of all the components within the configuration, all the technology that's been applied to it. In this case, it's Advanced Propulsion Center's 2025 projections on lithium iron phosphate batteries produces a 203 kilowatt hour pack. That's what generates this configuration, which represents, this spot on the electrification spectrum. But volume is just one characteristic. Mass here, actually the mass doesn't take too much of a hit, really similar to a legacy, but would start going up from here. But then cost is always an important KPI to look at. So here's interesting results of the legacy cost, and these are the conditions, that total cost of ownership conditions. I'm including 15 years of doing this cycle once a week for this 15-year life. If you change that, it's going to affect the results, and you can see the results update there. It's not going to affect the mass or volume, but it will affect the total cost of ownership, as efficiencies of each and every component through this cycle are going to be calculated and included. The initial cost here, so actually the initial cost, it's pretty interesting how you get from the legacy to the series hybrid. Are actually able to save total cost of ownership And where does that come from? Transmission savings and engine downsizing savings is really the most contributor. The total cost jumps and includes fuel. So really achieving the same efficiency, fuel economy, because you're not seeing a huge gain or loss delta in fuel. So it's interesting to know that while going to a series powertrain, it includes increasing the efficiency of the internal combustion engine, but it also includes decreasing efficiency of this electric only path. So there's counteracting forces, and it's kind of neat to be able to see how those counteracting forces change things on the electrification spectrum. So this here is really total cost of ownership advantage. If you wanted to look at the parallel version, which gets very close on total cost of ownership, we can also look at the details of this. This is the breakdown of the cost. If we wanted to look at, customer really wants to know the breakdown of the volume, since we need to include that. Here's the difference between the parallel and the series as far as the different component volumes. Total cost of ownership between those two. But really, if we go back here and compare it to the legacy, series to the legacy, it's an interesting breakdown. See how adding the battery, you're able to downsize the engine. Fuel tank, essentially the same total volume. Fuel tank also stays remarkably the same. Even though these are very different powertrains with different efficiencies at different component levels, the results, you can see resolution of the breakdown of applying these technologies to uniformly to each powertrain. You can see this is the solution that's probably going to submit in the request for powertrain proposal, and we have the data to back it up.